Nobody? Is everybody done with the homework? What? Number 16. Oh, this is the one that you were looking at with Patrick, right?
I tried what was on this paper and it didn't work. Except for like one version of the practice problem. But it doesn't work for anything else.
So in my little thing here, it says that this problem on average takes students around the world who are doing it 62 minutes. That's too long. Except it's not showing me what the problem actually is. There. 16. Okay, so this problem is actually a little bit, it is actually easier than it looks from the outset, I think. I actually went over how to do this yesterday, and I didn't actually plug in any answers, so I don't know if the code matches the problem. But whenever you have a sun behind me, I get to see how bad my haircut is. I got my hair this morning myself in 5 minutes. Really shows. Okay, whenever you have a chart that shows you the distance on the x-axis and the force on the y-axis here. This is a force displacement chart, force displacement graph at the top. And it gives you some function out here. The area under the curve is equal to what? Whenever you take the area under a curve, it's always the x times the y, in essence. Right? So that's force times distance, which is work, right? So the area under this curve is the work. The reason that we use the integral is because it's difficult to calculate the area under a curve, you think. If it's flat, it's easy. It's just a rectangle, it's just force times distance. If it's a triangle, that's not too bad because that's just force times distance times 1/2. If it's made up of triangles and rectangles, we can do that too, which this one is. So that's what we'll do. The only thing that you have to be kind of careful of is that when you have areas underneath and areas over the top, like this, any area underneath the x-axis is going to be negative work. In other words, work that is being done by the system and it's losing energy, so that ends up being a negative area, you can think of it as, okay? So in this particular chart, we have a negative area from 0 distance until 5.5 distance, 5.5 meters. And then at 5.5 meters on, we have positive work, all right? So how are we going to use this to figure out particles' speed? Well, that's a very good question. First of all, we're going to need to know how fast it's going to begin with, which they do tell us right here. At x equals 0, the velocity is 4.5 meters per second. So when we're right here, the velocity of this thing is 4.5 meters per second. During this entire time, then there is a negative force on the object, which a negative force is going to do negative work. Essentially, you can think of it as the object is doing work on its environment, so it's losing energy. So during this entire time, it's going to lose energy, and it should slow down until it gets up to this point where it has actually positive work being done. So how do we deal with this? We can deal with this in a couple of different ways. You can actually use kinematics to do some of this part. You can use kinematics to do this part right here, for example. because it's a constant force, which means it's a constant acceleration. Kinematics is good when you have constant acceleration. Once you get to this point, though, it's no longer any good. Can't do it. So what do we have to do if we're not going to use kinematics to do the first? We might as well not use kinematics because you can use energy to do all of this. How do we use energy? Well, we go to our book and we remember our energy equation. Go down here to conservation of energy. Conservation of energy equations look like this. The non-conservative work is equal to the change in kinetic energy plus the change in potential energy, or the total change in energy. Okay? The work that is being done on this object, because it is done negatively on the object, is non-conservative work. Non-conservative work is always work that is done work that is done against the object's motion. So that's where we'll put our non-conservative work. On this side, we'll put in our kinetic energy, which we know, because they tell us the velocity to begin with. We know our initial kinetic energy. And we're going to solve for the final kinetic energy. Where did we go? Here we go. That's not helping. Here we go. So during this whole time, and they want us to know what is the particle speed at x equals 2, which is right in here. So during this time, or this distance between 0 meters and 2 meters, there is a change in kinetic energy. What is that change in kinetic energy? It's due to this work that is being done here, and it turns out to be negative work, so we plug it in as negative work. Negative force times a distance of 2 meters. The force is negative 5. And so we get this. We get an initial velocity. I think, what was mine, 2.2 or something, whatever it was. I'm actually just not even going to plug in numbers. But what we have is we have work of the non-conservative forces equals change in kinetic. And it doesn't tell us that there's any change in height. So we're going to assume there's no change in height, no delta U. So the change in kinetic energy is 1/2 mv final squared. The final squared is the one we're trying to calculate. Minus 1/2 mv initial squared. We know our v initial, we know our mass. And the work is equal to the force times the distance. And the force in this case, remember, is negative. It's not a positive number, it's a negative number. And so we solve this equation for V final. And we know everything else in the equation. That'll get us part A. Is that how you did it?
No, I used the kinematics equation.
So the kinematic equations are fine to use at the very beginning, but at the very first part will work because you have a constant force, constant acceleration. Part B, it's not going to work. Okay? Did it work for you in part A? You get
It worked in part A.
Yeah. Okay. So that's what we would expect. We would expect it to work in part A, but we would not expect it to work in part B. So how do we do this in part B? Well, we do the same thing in part B. We do work equals change in kinetic energy. But now we're going to do, let's see, they want us to do the particle's speed at 5.5 meters, which is way over here, where it crosses the 0 point, right? So we have to do this big change now. We need all of the area under this curve, right? Now the area under this curve is equal to the work being done, and it's a big rectangle, which is -5/4, so that's -20 joules of work there. And then we have this triangle here, which goes 1.5 times 5 times -5, and then you have to multiply that by half because it's a triangle, right? So if we do the math really quick, we show our little thing here, boop, like that. We're going to split this into two things. This is -5 by 4. So this equals negative 20 joules of work. And this one is 1.5 by negative 5. And we have to multiply it by a half because it's a triangle. 1/2 times negative 5 times 1.5. What is that? That's going to be 7.5 times a half, which is 3.75. Sound right? 3.75. And that's a negative. Negative 3.75. So what we've shown you here, whoa, that's a big negative sign. What we've shown you here is an alternative method to doing calculus in very simple situations. And we do this in the algebra-based version of this class as well, where we have a curve that shows us the function, the force function, as a function of distance, but we don't want you to have to do the calculus, so we teach you how to calculate the work using areas. So this is now our work for the second part, and since we did this from all the way from here all the way to here, we still have the same initial condition, or the same initial speed for this equation. So we put it on our initial speed the same way we did before, which was in my case 2.2 or something like that. But in this case, the work over here, the force times the distance over here, becomes this number instead. Right? This and this would be the integral becomes this, I guess. But it's just the adding up of areas. And in calculus, that's exactly what doing an integral in 2 dimensions does, is it calculates the area under the curve. And it even comes out with the negative sign if you do it properly. It even brings out that negative sign through the calculus. So it's all in the math. The math knows how to do the physics, because the math was created by physicists to do the physics. So then you solve the equation again with this new work in place of this thing on the left, and then you go ahead and you get your values out. Now, like I said, I didn't actually work the numbers, so I don't know if that brings out the correct answer. I should probably do that really quick, because I didn't. Let's see, what is my initial? No, my initial is 4.5. Why can't I remember simple numbers? Don't have room in my brain. My brain's too small. So mine is 4.5. If I have, I have a calculator here somewhere. Here we go. By the way, if any of you need calculators, I have them in this front drawer. 2 or 3 of them. So if we go here, we start off with our 4.5. We have our initial velocity of 4.5. We square that. How do you square things on this? Just multiply it by 4.5 again, I guess. And then we have our mass of 4.8. Oh, shoot. Yeah. 4.5 times 4.8 times 0.5. So that gives me 48.6. And then I'm going to add to that. No, I'm going to add that to, I'm going to subtract 23.75. Then I'm going to divide by 4.8 times 2. And I'm going to take the square root. Where's the square root? There's the square root. Square root of the answer. So in this particular one, I get a 3.21 at 5.5. So I'm going to enter that in and see if it works. Don't know if it will or not. Oh, I can't actually enter in answers here for some reason. I thought I could, but I can't. But let's go to $16. Yep, that is correct. It's actually 3.22 because I rounded down instead of up. But that will give you the correct answer for that one. And then the next one again, it's asking for the particle speed at 10 meters. So you go out to here and you go in this graph here that has this dotted line that assumes that this thing keeps going on all the way out to 10 meters. So you, in the case of the 10 meter one, you have to add the area here and then subtract the area here. Because this one's going to be positive area, this one's going to be negative area, and that will give you the right answer. Now, that is a lot of kind of doing math by intuition, but does it make sense? Did I explain it well?
And I think I wasn't getting it at all from the paper because I couldn't really tell like what areas we were supposed to do and like what we were supposed to take from different places.
So rule of thumb in calculus is that area between the curve and the x-axis is the integral. So a lot of people like to say the area under the curve, but it's actually the area between the curve and the x-axis. So if your curve is below the x-axis, then you have to take the area above the curve. But that's always going to be a negative area because it's under the x-axis. It's below the x-axis. So that ends up being a negative value. And that was part B. And then in part C, you have both areas below the curve and above the curve, or below the x-axis and above the x-axis. In which case, the above the ones are positive, the below ones are negative. You add them all together, and that gives you the total area, which in this case is equal to the total work. Does that kind of make sense? And we'll use that again. There are other situations in physics where we use integrals to calculate things, but it's actually a little bit easier to skip the integration, to skip the calculus, and take advantage of the simplicity of the function to calculate that area. It's not always simple because what if we have, like earlier, I think I gave you a force function that is, I think there's one in number 2 or something that's a quadratic. You can't calculate the area of a quadratic very easily just knowing some formula. So you're going to have to do the integral. Luckily, the integral of a quadratic is really simple. So the only situations where we do this in physics is when you can break down the curve into a bunch of rectangles and triangles so that it makes it easy to calculate. If you can't break it down into rectangles and triangles, it's not worth doing. Here's my question for you. Does it make sense why part A worked with kinematics?
Because it's a straight line and it didn't come from a not straight.
Yeah. So if it's a horizontal line, that means the force is not changing. It is a constant force. Because of Newton's second law, if you have a constant force, you will always have a constant acceleration. Constant acceleration means that kinematics can be used. That is one of the assumptions of kinematics that you kind of have to keep in your head all throughout this class. Because we use kinematics at the beginning as if it's kind of the thing you always use, because we use it a lot at the beginning of the class. Like it's a big deal. But the problem with kinematics is it only works in that situation. It only works if you have a constant acceleration on your object. Or no acceleration, which is also a constant acceleration. Right? So, yeah, if you don't have a constant acceleration, you can't use kinematics. So anytime the force changes in distance or changes in time, it can't be used. So that's kind of the kicker there. And you could actually use it over here as well, if you wanted to, where it's constant again, but then you would want to know what your speed is right here at the beginning of this constant part, because you'll need that initial speed. Otherwise, you're kind of in trouble. You always need to know the initial speed when that constant force begins. If you don't know the initial speed, then you won't be able to get much out of kinematics. Okay, does anybody have another question? Did I answer that well enough? Any other questions from other that you want to work on? I love this one. In the movie Monty Python and the Holy Grail, how many of you have seen that movie? If you haven't seen that movie, it's worth seeing. but only like late at night when your brain is completely fried and you're so tired that anything is funny. Then you gotta go see that. All right. So in the movie The Monty Python and the Holy Grail, a cow is catapulted from the top of the castle, the French castle, in fact. Oh, on the top of the wall, so the gravitational potential energy is set to 0 at ground level. The cow is launched from a spring with a constant 1.4 times 10 to the 4th Newton per meter. It's pulled back 0.3 meters. If the castle is 9.5 meters tall and the mass of the cow is 140 kilograms, what are the following? The gravitational potential energy of the cow at the top of the castle, that's of course easy. That's just mass times gravity times height. The elastic spring energy in the cow, before the catapult is released. That one, the spring energy is always equal to 1/2 kx squared. Right, so you plug that in. And then the speed of the cow right before it lands on the ground. This one, again, is going to require the energy equation. So here's our castle. I wish I could draw this like it is in the movie, but oh well. Here's our cow at the top. Little tail. At the top of the castle, the energy is, and then we got the spring as well. We have two kinds of energy. We have potential energy, cow's potential energy, which is mgh. And we also have spring potential energy, which is 1/2 kx squared. After it's launched, the spring kinetic energy becomes, the spring potential energy becomes kinetic energy. And then as it falls, the gravitational potential energy becomes kinetic energy. So at the bottom, all of it is kinetic energy. And the kinetic energy is equal to 1/2 mv squared. There's no potential energy at the bottom, no spring potential energy at the bottom. So these ones have to equal these ones. We know everything in this equation except for v. So we solve it for v. No friction or anything else involved. It's a frictionless cow. And most of the problems are similar to that, where you start with some group of energies, some combination of energies, you end with some combination of energies. Those two things have to be equal, and there's usually one thing that you don't know. Solve for it and you're done. Which I think is much easier than going through 2 or 3 kinematic equations and 2 or 3 unknowns. How did everybody do on the first 3 problems, which I think are some of the more challenging ones in this assignment? Or the first 2, probably. Is anybody still struggling to get the first 2 done, where we're using vectors and a little bit of calculus? Or did we get those cranked out? Any other problems throughout the rest of the assignment that you want to work on?
Number 11.
Number 11. Well, these ones are classic. In the figure below, the 2 boxes are initially moving with a speed v. So this one's moving up, this one's moving this way. And this actually confuses a lot of people. They say, well, how could the boxes be moving this way? Naturally, the boxes would move the other way. It doesn't really matter how they're moving, they're just telling us that they're moving. It could be somebody lifted them up, pushed, somebody might have pulled on this one so that it's originally moving this way. Whatever, it doesn't actually matter why they're doing that. You just have to recognize that initially they're moving this way, and they will eventually start moving back the other way, because gravity's going to pull on this one and pull it back this way. However, I was going to say we're going to deal with friction, but we're not. It says right here, ignore friction. So we're going to ignore friction. There's no friction. We're going to determine the expression for distance the boxes travel for coming to a rest. And the floor is the position for 0 gravitational potential energy. I don't like the way that's actually worded, because if there's no friction, the top one's not going to come to a rest till it goes over the edge and falls down to the bottom. But well, wait. We'll talk about when box 2 comes to a rest. That'll make it a little bit simpler. So we're going to talk about when box 2 comes to a rest, ignoring friction. We're determining an expression for the distance the boxes travels. Choose the floor as a position for 0 gravity potential energy. Use the following as the necessary. Okay. So at the beginning of this system, when this system starts off, what kind of energies does it have? It's starting, where is it starting, first of all? It's starting at 0 here, and at some position here, right? Whatever this position here. Where it is in the position here doesn't change its energy at all. But where it is in its position here does change its energy, right? So we start off by saying, well, at the very beginning, all of the energy is kinetic because this one is at the bottom at 0, and this one is at the same height all the time, so it doesn't change its potential energy. So the potential energy is all 0, and the only other kind of energy that's in the system is kinetic energy, movement energy. So all the energy at the beginning is kinetic energy. But then it becomes potential energy, right? It's going to become potential energy as it goes upward. And it's going to go upward, and as it goes upward, the potential energy, the kinetic energy is going to become potential energy until the kinetic energy runs out. So how do we imagine this? We imagine this kind of by saying, it's kind of like saying you have this glass full of water. We're going to be a glasses completely full kind of person today. We have this glass completely full of water, which we're going to call kinetic energy. And this is when the first mass is at the bottom, second mass is wherever it is, and it's moving upward. All the energy is kinetic. And then we're going to pour all this energy into a different kind of energy at the end. Because at the end, where it's stopped and it's kind of suspended above the ground, here's our table now, right? Now it's suspended above the ground at some height, h, and it's stopped. When it is stopped, all of this water that's been dumped out of this first glass into this other glass is now potential energy. But it's the same amount of water, right? So everything is kinetic energy at the beginning. There's no potential energy at the beginning. So all the energies added together at the beginning is the kinetic energy initial. All the energies added together at the end is the potential energy initial. Well, how do we write these things down? Or, sorry, potential energy final. But how do we write these things down? Kinetic energy initially is 1/2 mv squared, but what is the m of this system? How many masses do we have? We have 2. 2 masses are moving, and they will both contribute to the total energy of the system at the beginning. And then the velocity of those 2 masses squared. Same velocity because they're tied together, right? But at the end, it's a little bit different. Which one of these is contributing to the potential energy of the system at the end? Only this one. This one hasn't changed its potential energy at all because it hasn't changed height at all. So at the end, it's only the m1, if we call this one 1 and this one 2, I don't know what it is in the book. It's only m1 times g times the height of m1. And then what you're solving for in this is the height. Does that make sense? And all of these questions are this way, with every one of them has a little twist in it. The twist in this one is that the kinetic energy on the one side involved both masses, but the potential energy at the end only involves one mass. That's because the other mass didn't change height, right? It just slowed down. Where did you have a question? Because you were kind of, this is like an auction. If you make any movement, you get the next bid. I went to an auction a few years ago for some athletic equipment at the college, and they had one of these like traditional auctioneers that speaks really, really fast and uses all these words that mean nothing. And I'd never been in an auction like that before. I couldn't understand what he was saying. I didn't understand what all of his gestures and words meant. And so I kept bidding, and he kept saying, "You have the high bid." But I didn't even know he was saying, "You have the high bid." So I just kept bidding because I thought people were outbidding me. Because he just kept talking, and it was just kind of funny. At the end, people were kind of giggling at me for being this city boy that's never been to a traditional auction. But I got what I wanted. Well, anyway. Now I need an exercise bike to put in my office. Getting fat. Any other questions?
For like other problems?
Yeah, or this question or anything. This question, did you understand how this is done? Okay. Yeah, any other questions on any other problems?
Um, 13.
13. Air resistance is negligibly. So we have a a sphere, mass m, launched horizontally over a body of water, height of h above the water, launch speed v0. Determine expressions for the following in terms of m, v, h, and g. No air resistance. We want to know the amount of work done by the force of gravity on the projectile during its flight. We want to know the change in kinetic energy of the projectile from the time it was fired until it hits the water, and find the final kinetic energy of the projectile as it hits the water. Right? Now, the temptation with this kind of problem is to revert back to vectors and kinematics. But this kind of a problem where you're given the total energy at the beginning, and you're given all the information you need to figure out the total energy at the end, you don't want to go with kinematics. You want to go with energy, because energy is much simpler. So let's do this. So here's our water. You know, if I was a really good teacher, I would like use different colors. I know that I can select different colors. Here we go. So water would look more like water. Here's our water. And we'll make our sphere pink because it's a nice color. And our sphere is launched, you know, horizontally, I think it said. Horizontally, yeah. So it's launched horizontally this way with some velocity v naught. And it's launched at some height h above the water. And so what we're going to do is we're going to do what we always do. We're going to calculate all the energies at the beginning and all the energies at the end. What kind of energies does it have at the beginning? It has potential energy equal to what? Right? mgh. Mass, gravity, height. And then what other kind of energy does it have at the top? Kinetic equal to what? Like that, right? Any other kinds of energies up here? Not really. Those are the two energies we've got. At the bottom, we're going to call this elevation here, we're going to call this h equals 0. So does it have any potential energy at h equals 0? No, because h equals 0, right? But what other kinds of energy does it have? So it's fallen down, and now it has a velocity in this direction. V final. So what kind of energy does it have? Kinetic again, right? This is kinetic initial, potential initial, kinetic final, 1/2 mv squared again. Remember that energies don't care about the vector quantity. It doesn't care that it is turned. It just wants to know how fast you're going, right? So this v is actually a speed. Why they use v in these books, I don't know, but they do. Some books use u to demonstrate that it's a different thing than the actual velocity, but it should be known that it's a different thing anyway because it's squared, and you can't really square a vector in this way. So this is the speed of the object. And no other energies, everything else is 0. So these energies have to equal these energies, right? So we add these to the beginning, mgh. Oh, sorry. Then they want to know the amount of work done. The amount of work done. Work can only be done in a system if it's not an external force, if it's not something on the outside pushing it, or even if it is now something on the outside pushing it, actually, in many cases. But the work is done from potential energies. Potential energies are the things that have the ability to do work, right? You can have external forces do work as well, like somebody pushing. That's not necessarily a potential energy technically of the system. But when we're talking about the enclosed system or the isolated system like we do in these situations, the only thing that can do work are the stored potential energies can do work, and at least conservative work. Non-conservative work, of course, can be done by friction. Friction can do non-conservative. You're looking at me like that's like crazy talk. Are you understanding what I said, or is it just boom? Okay. What are you talking about? Anyway, so in this case, the potential energy, the gravitational potential energy can do work. And so it's going to do work speeding up this ball. This ball is going to be going faster down here than it was up here. And that faster is going to come from this. And all of this is converted into kinetic energy. So this ends up being the work done. So that's part A, already done. Right? Part B, what does it ask for? Part B is the change in kinetic energy. Well, the change in kinetic energy is equal to the negative work, essentially, right? So the work, and the work is equal to negative the force. But anyway, the point is, negative the force times distance. But anyway, so it's the same answer again, mgh. It's the amount of work done is equal to the amount of change in kinetic energy. And then what is the final kinetic energy of the projectile? Well, that's all of that energy added together at the end, which we already wrote down. We just didn't add it together. So here is the kinetic, here's all the energy at the beginning. Here is all the energy at the end, but they want us to write it in terms of m, v naught, and h. We don't know what v is, and so we can't write it down this way because we don't know what v is. They want to know in terms of v naught. So we write it down in terms of mgh plus 1/2 mv naught squared, and that is part C. And that, I think that's really the big confusing part there, is that most people write 1/2 mv squared, but they didn't tell you you could use v. You can only use v naught. So since m1 1/2 mv squared is equal to 1/2 mv naught squared plus mgh, you can just write down the other side of the equation. And then, are any of the answers changed if the initial angle is changed? Doesn't matter. Doesn't matter if it goes down or up or anything else, really. It doesn't really change it. It will all be the same thing, which is kind of nice. As long as you're not asking anybody, what is the angle of the ball as it enters the water? If they ask you that, then you're stuck. You got to go to kinematics, and oh well, such is life. Any more questions? By the way, for STEM Club, I just bought, you can see, I just bought a bunch of soda, so if you want a soda, have a soda and then wash off the can and leave it in the back. And then we'll have enough cans for we won't have to go scrolling. Okay, which flower shop is it? Okay. Cool. Are you going to pick them up, or do you need me to pick them up? Okay. We'll need a good 50 or more flowers, pretty long stems. I prefer them not trimmed down so that the kids can be far away from the liquid nitrogen. I ordered the liquid nitrogen, and I got all marshmallows and chips and all that stuff, sugar. Oh, I was trying to make rock candy using soda yesterday, but it didn't work out, it doesn't look like. I don't think I have a saturated enough solution. I wonder if I need something to kind of start the process. Maybe more sugar. betcha. If we dip this in some sugar to get some crystals, it'll work.
Would you mind signing my grade sheet?
Did you have to do that last year?
Not near as often because Miss Higgins is running, or
Yeah, she's kind of. You think they would pose her for that? She's the one that's pushed every athlete with us all the time. I think it's kind of ridiculous for everybody that
I think
How do you do?
stick with.
Well, I was assuming you could, and I was hoping you can, because that would be cool to have carbonated rock candy.
I just wondered if it
And I added sugar. What's that? All you really need is a supersaturated solution, so I added a cup of sugar to it.
what about the acid inside of the soda?
It doesn't really matter, because table sugar is not a single kind of sugar. Table sugar is made of like 4 different kinds of sugars, including glucose and fructose. It's not like this. Most sugar is made from beet sugar, and beets have several different kinds of sugars in them. And this actually has, this bag of sugar has 8 grams of added sugar to it per serving.
And extra sugar.
Yeah, it says right here, it includes 8 grams added sugars. That's hilarious. Yeah. There's no vitamin D though. And no saturated fat. No, I don't really know if it'll work with, it's my understanding, and I was talking to Aaron about this yesterday. It's my understanding that you can do it with any supersaturated solution. You can create crystals. But I didn't take into account the fact that sodas do have some things in them that might deter the reaction. I didn't think about that. There are some acids for sure. The carbon dioxide, I don't know if it would cause a problem. I'll see if it would. So that's to the last question for the work done on box by the group. Oh, sorry. Which one is box 1? The top one, okay. That I didn't answer that question because I forgot that they asked that question. So you have to the work done on box 1 by the rope. That means you have to know the tension in the rope, the force that's exerted in the rope, right? And
I figured out what
you figured out how to get the answer?
I figured out something that I did wrong.
Oh.
I forgot the subscript, but I would like to hear what you were saying.
So you have to figure out what the force is in the rope, and since there is no friction, there's only one force on this rope, and that force is from this box. Right? This box is exerting a force of m times g on that rope. Right? That means the tension in the rope is m times g. That means the work done is m times g times the distance that this box moves. Right? So, what is the... And they want you to use m1, m2, v, and g for the work done. So they actually, what is v? Is v the initial velocity or the final velocity, or just the velocity at any point?
like
Oh, it's-
labeled the same.
Well, it's the initial velocity actually. It says initially moving with a speed v. Expression for the work done on box 1 by the rope using M1, M2, V, and G. Um, M1. Let's see. Kinetic energy. Okay, I see what they did. It would actually work either way. Um, the force downward is equal to M times G, which is equal to the tension in the rope. So the tension in the rope here is M, which is M2 times G, right?
Dots on top is M1.
Oh, but M2 is the thing pulling on it. So M2 times G gives you that force pulling on it. And if you do M2 times G times the distance, but they don't give you the distance, right? They don't give you the distance, which would actually be equal to the height, but they don't let you use the height either, right? So this is true, but you can't use it. But what is this also equal to? This is equal to the work. This is also equal to the change in kinetic energy. And the change in kinetic energy is the kinetic energy final minus kinetic energy initial. And the kinetic energy final is 0, right? So it's equal to this. And work is actually equal to negative kinetic energy. So this is actually, your work is actually equal to your negative initial kinetic energy. In this case. So the initial kinetic energy is 1/2 mv squared. So that's their justification for that. Make sense? So a lot of this stuff in this chapter is just kind of going back and forth between these different energy equations. You have the work equals change, negative change in kinetic energy, the work equals the change in potential energy. And the potential energy, negative potential energy equals the change in kinetic energy. And then the big one, which is the non-conservative work equals the change in potential plus change in kinetic. It's just a lot of back and forth between these equations at the beginning of the system, at the end of the system, things like this. It's just back and forth, like ping pong. You want to do that one?
Yeah, if you don't mind, I know what the cost is.
That's all right. Which one is it?
19.
Let's do that. So we have a block of mass, 200 grams, is attached to a spring. Spring constant 86. Other end of the spring, support of mass, rough surface, coefficient of friction. So we got friction. It's inclined at an angle of 30 degrees. Block pushed along the surface, spring compressed by 12 centimeters and released from rest. So this one's a little more involved, obviously, especially because it involves friction on an incline. Because this is going to require us to do a little bit of force and vector stuff before we get started, because we need to know how much friction there is. And we can only calculate that by calculating some things using the incline. So here's the incline. Here's our box. Here's our spring. And the forces are involved. Well, so the spring, it's going to be compressed. They tell us that it is going to be compressed. They're going to tell us that this is going to be compressed some distance d, that it's going to be compressed by when they squish it down this way. They're also telling us that Okay, so I just had to check a few things. So, they want to know the speed where it crosses the point. So this is the point where we're going to call the x equals 0, or we're just going to call this the 0, 0 point. X equals 0, y equals 0 point. And down here is where we're going to compress it to 12 centimeters this way, or whatever it is for your particular problem. We're going to compress it down to this point and then release it from this point. Down at this point, they want to know what is the potential energy from the spring. What is the spring potential energy when we've compressed it this much? And spring potential energy is equal to just 1/2 kx squared, where the x is how much you've compressed it, right? And they've given us the x, so that's part A. That's pretty easy, right? Then they want to know the speed of the block when it gets back to the point where it started. So when you compress it to here and then you release it, and when it gets back to this point, how much speed does it have? Well, that means that all of your potential energy in your spring has become kinetic energy, right? So you do 1/2 kx squared equals 1/2 mv squared. But let's check something really quick. We probably should take into account the fact that we're going to lose some energy in friction along the way during that short span there. So we have some friction that's being burned up there. So where does that go in this equation? Well, you can go back to doing the problem like this, where the non-conservative work, which is where you'd put your friction, equals your change in kinetic plus change in potential. But you can also kind of shortcut it by looking at this equation, because this equation is a version of this equation, where we've moved the kinetic to one side and the potential to the other side. We've moved the initial kinetic and initial potential to one side. So we have the initial potential is here, final kinetic is here, but we've kind of lost track of where this was. Whenever you're doing this, if you have friction, it's going to take energy out of the system at the end. So this is the end of the system. And so we just kind of subtract off the friction right here. So we subtract off the work done by friction here, the non-conservative work. And the work done by friction is equal to 1/2 mv squared minus the force due to friction over the distance of that friction. Well, we know the distance. The distance is the amount that we stretch the spring, so we know that part. We just don't know the force of friction. This is the part we need to figure out now. So we go back to our diagram. We have the weight, which comes straight down, mg, right? And so we have this triangle here, which has this angle, which is the same angle as this one, right? And we have these two forces. We have the downward force, which is equal to the normal force. And that's actually what we want to know. We want to know the normal force. Because friction is equal to the coefficient of friction times the normal force. So we need to know this one, which is right next to the angle. So that is equal to mg times cosine theta, because it's next to the angle theta. So friction equals mu times m times g times cosine theta. And now we can solve for part B. That goes in for little f right here, and everything else we know. And we solve for velocity.
So the P would just be the 12?
Yep.
Okay.
And the same thing goes for part C. In part C, they want us to measure the position of the block where it comes to rest on its way up the incline. You use the same equation we just did, except you plug in V equals 0 here, and you solve for D instead. Does that make sense? Yep. Yep, this is 1/2 kx squared on the left side. So in that case, this first term goes away because V is equal to 0. And the energy that you had in the spring becomes all energy going up the ramp being taken away by friction. So this equation gets you both B and C, but in different ways. Make sense? Okay. Any more, or are you good?
Well, if you're going to stay, I'll have you classes till.
I'll answer questions. This is my office hour right now, anyway.
Okay, how about number 8?
Number 8.
Reminds me of what I did. I would just hassle them
Yeah.
constantly with questions.
This is how you get through physics. This is there are 2 things you must do to get through physics. You must work together with people on your homework, whether it be fellow classmates, tutors, or your teacher. And you must ask questions constantly and assess them. That's how you survive physics. Those are the keys. And really, that's how you survive all difficult classes. It's just that most students don't really encounter that difficult class in their freshman year. Most students are taking really easy general ed stuff that's not that hard to get through. And but when you're going into sciences and you're taking physics or calculus in your first semester or first year, it's a little different experience. All right, so what is number 8 anyway? Number 8, you said? Particle of mass 2.6 moves under the influence of this force. Ah, yes. Okay, so this one is actually a calculus one. I gave you another calculus one. I forgot to. Okay, so for you guys that are in the calculus part of the class, I want you to do number 8. Can you guys go do number 8? Wait a second, I gave 2 more. Number 7 as well.
Yeah, I was going to ask about number 7 next.
Yeah, I want you guys to do number 7 and number 8. Sorry. I'm adding to your troubles. Number 7 and 8 are both calculus problems, for sure. I think that's it, though. Okay. So this one goes back to, you have a force that is changing, and you need to calculate you need to calculate the work done between 2 points. So they've told you the work, the speed at one particular point. They want you to calculate the speed at a different point. And so what we do is we do our integral. Let's see here. There's actually 2 ways to do this problem, I believe. And I think they'll both give you the same answer. But let's check to see if that's correct. The first way to do this problem is to just go through and do the integral just straight up. You have the integral of f dot dr. This integral in one dimension, because we're only moving in the x dimension, we're just moving straight forward, becomes f dx. Function of x, function of force times dx, like this. Right? And so our function is whatever it is. It's 5x squared, minus 5x squared plus 7x. So we have the integral of minus 5x squared plus 7x dx. Right? How do we know this becomes this in one dimension? This thing becomes this thing in one dimension? Because f dot dr becomes always this. It always ends up being the x part of the function times the x part of r. And the x part of the y part of plus the y part, sorry, times the y part of r. And since our path is one dimensional, the x part of r is just dx. dr. So anyway. Okay, so so we do this integral. The integral of negative 5x squared. We're gonna end up with 5x cubed negative over 3, right? Plus 7x squared over 2. And remember that when you're doing this, you either have to have limits here and here, or you have to add a constant on here. Now we can do it either way, because they've told us the limits, we're going between 3 meters and positive 3 meters. I think we can do it this way. But we have to check. We have to check to see if this function right here, 5x squared, or sorry, this function here gives us the answer they told us it gives us. So if we plug in negative 3 into here, negative 3 cubed over 3 plus 7 times 3, negative 3 squared over 2. If this is equal to the initial velocity that they gave us, which in my case is 28 meters per second, then we're good. If it's not, then we can't do it this way. So we'll check real quick. So negative 3 cubed is negative 27 times negative 5. So that gives me negative 45 plus 9 times 7 is, what is 9 times 7? 63 over 2, which is 30. That's 63 over 2 is 31 and a half. 45 minus 31.5. That doesn't seem to be correct. It should give me 28, but it gives me 13. So this does not equal 28, so we can't use this method. It's not equal to our initial conditions. So what we do is we go back to this function here, and we add on the constant, which is our initial velocity. So we plug in our distance, our x, our final x into here, and then we add on our initial velocity, and that will give us the answer.
Okay, so you plug in the final?
The initial velocity and the final x.
Oh,
That's correct. And that should be correct.
It's a weird angle looking at
Yeah, eventually they'll have 2 screens in here, which will probably be after you're not taking physics anymore.
it.
Not only 2 screens, they'll probably have 4 screens in here, 2 up here and 2 back there. Turning this into a distance learning lab.
going to do number 7?
Okay.
That's the last one.
So number 7, same idea with part A. It's moving in x, completely in the x direction. So it's the same thing. You're going to do the integral of this with respect to x, and then you're going to plug in from x3 to x5. You're actually going to use those numbers as your limits that time, because they've told you the beginning and end, and they haven't told you anything different about the initial. And they just want to calculate the work done. And then picking a convenient reference point of the potential energy as to be 0 at x equals 0, find the potential energy for this force. In this case, there's that's what x, assume x and joules, x and meters do not include units in your answer. I think this is actually kind of a bad way to word this question. I think that they need to say that this is being done against friction or this is being done against gravity, and then they could say that this next part is right. But I guess we just make that assumption, which is fine too, I guess. But in the case of work, doing some kind of work, doing the changing this object's potential energy, work is equal to change in potential energy. So it should actually give you, this actually is the answer you get when you do the integral on this, right? When you do this integral, this is what you get. Except for the signs, because it's actually equal to negative. The work is actually equal to negative change in potential. The work equals negative change in potential. So you have to change the signs, and then you're back. And they don't want you to plug the numbers in, they just want you to give the actual value. Does that make sense? All done? All done? All right. Well, crank those out, and if you have any other questions, feel free to come by or call or email or whatever. You guys have any questions? So raise your hand if you feel like going through physics with calculus is mostly about like jumping through hoops. That's how I felt too my freshman year of calculus physics, because it's so much, so many numbers and so many just calculating things and then writing down numbers. And you really rarely get a chance to actually solve problems. Like this chapter, I think, is the first time you really get to solve a problem using calculus. That makes sense, but you don't really do that much of it. You only do a couple of them, and it's back to just number crunching. But that's the way it is. Sorry, go ahead.
Could you go back to number 8?
Yeah. Chapter 8.
So we had that integral on, we had the velocity and
Yeah. So remember, whenever you're doing integrals, you essentially have two options. You either have the indefinite integral, where you don't know the where you're going, or you have the definite integral, where you definitely have the starting point and ending point, whatever it is, right? Now, at this point, at this problem, they do give you a starting point and an ending point, but the problem is at the starting point, you have some initial velocity that's not included in the function, which can happen in real life. So when that happens, you either assume, you can do one of two things. You can assume that that initial velocity is not going to be included in the function, and just do the math, and that will give you the right answer no matter what, which is what we did second. Or you can plug in these values here and see what it gives you. And see, like, you plug in this value into the answer of the integral, and if it equals the initial velocity that they give you, then you're good to go. You can just do it. You just can do a definite integral. It doesn't really matter one way or the other. I just wanted to see what they were choosing. So I would actually just do the indefinite integral every time if they've given you an initial velocity. So doing the indefinite integral on some polynomial, you get out some polynomial, and you do you don't do your integral. You don't do your integral calculation or your evaluation of the integral. You just get some like x squared over 5 thirds or whatever it is, plus x over 2 or something, whatever you get, and then you always have to add that constant on, right? No matter what happens with an integral, if you're doing an indefinite integral, that constant is your initial condition. That's where the thing starts. That's your zero value.
So I don't know what values to plug into that equation.
And this, you plug in your end values, your final x position into this, and add on your initial velocity.
Which was 28.
No, your initial velocity is, in my case, my initial velocity was 26 in this one, but they want to know the speed at 2.2, and so that's your final position. So you plug in 2.2 in for x, and then you plug in 28 here.
Okay.
That make sense, man? So whatever it is you're calculating. Oh, actually, you know what? I lied to you. Sorry. I think I lied to Colin too. This is actually not going to. This is work, which is also equal to change in kinetic energy. So this shouldn't be, and this shouldn't be V. This should be 1/2 mv squared. Is 1/2 mv squared would be your constant, not V. Sorry. That's the difference. I should tell. I wonder if she just went to sit down with me.
That's gonna be still getting a fairly large number for that.
What's the number? What's the size?
So I got 1,097 minus 106 plus 56. I got 1,047.
Did you enter it in, or are you just not sure if it's? That seems like a reasonable number to me, because remember that joules are not a very big measure of energy. Let me check really quick. Oh wait, did you solve for the velocity when you were done? Because in the end, this is equal to, remember, changing kinetic energy. So the thing that you calculate when you do your calculation plus your constant length mv squared is actually equal to 1/2 mv final squared. So then you have to divide that whole thing by m, divide the whole thing by 1/2, and then take the square root. Probably gonna come in. And I think the key to this is that you have to seed it. Because I just seeded this morning and it's already growing crystals. So you have to like dip it in some crystals.
Could you see how far I'm off?
So did you do that calculation?
They're at a reasonable number, 27